Hello IB students. So last class we've talked about velocity, and this class we're going to talk about acceleration. All right, so acceleration is investigation of the change of velocity. So this physical quantity is the measure of how fast velocity is changing. In fact, its definition is the change of velocity of an object in a given period of time, right? So its definition can be explained by a formula, which is acceleration, denoted by the letter A, is equal to the change of velocity in a given period of time. Alright, so what is the change of the velocity? Well, it is the final velocity of the object minus the initial velocity, right? So for example, I'm now running 2 miles per hour, and suddenly I'm running 4 miles per hour, and I accelerated for 4 seconds. So my final velocity will be 4 miles per hour. My initial velocity is 2 miles per hour. So my change of velocity is 4 minus 2, which is 2. All right, so divided by time. So in that case, I accelerated for 4 seconds. So t equals 4. So this equals to 4 minus 2 divided by 4, which is equal to 0.5 meters per second. So what does this mean? So this means I am accelerating 0.5 meters per second. So my speed goes up 0.5 meters per second every single second, right? So this is the explanation of the unit. However, in physics textbook, they often combine the two s together. So it looks like this: meters per second squared. So you must write like this, but you can understand it that way. All right, so in other textbooks they may write it as 0.5 meters second to the negative power, and these two are mathematically equivalent. All right, and just like velocity and displacement, acceleration is a vector, because the change of velocity is a vector, because we've talked about the velocity is a vector itself. So the change of velocity is a vector. So acceleration is also a vector, which means it has a magnitude and direction. I can only say my acceleration is 3 meters per second squared forward. I cannot just say my acceleration is 3 meters per second squared. That will be very absurd, right? So it must have a direction, and if I'm accelerating 3 meters per second squared to the right, I am simultaneously also accelerating negative 3 meters per second squared to the left. These two are physically equivalent, all right? So how about deceleration? So I can accelerate, my speed can go up. What about if my speed goes down? Well, in this case, my final velocity is less than my initial velocity. This means, for example, if I'm running 4 miles per hour and I decelerate for 4 seconds and I become 0 miles per hour, which means I'm stationary, my acceleration can still be calculated by this formula, which is my final velocity, which is I'm stationary, is 0 miles per hour minus what? Minus 4 miles per hour divided by 4 seconds, right? So my acceleration is negative 1 miles per hour. To where? To the right, because I'm decelerating to the right? So my acceleration is negative 1 miles per hour to the left, which means I am actually accelerating to the left. So I'm running to the right, and when I decelerate to the right, I am actually accelerating to the left. All right, so think about it. You need to process this information. It's very important. All right, next I'm gonna introduce to you to the VT graph. So similarly to the DT graph, which we've introduced in the previous lecture, the VT graph, the curve on the VT graph basically gives you the information of the velocity value at every moment. For example, at t equals 2, my velocity is 2. And at t equals 3, my velocity is 3, right? So this is what it does. And using the VT graph, we can actually calculate the acceleration of this object that the graph is representing, all right? So let's say we want to calculate the acceleration between t equals 2 and t equals 3. Well, what we do is, we have talked about the formula A equals final velocity minus initial velocity divided by time, right? So my final velocity is 3 and my initial velocity is 2. So 3 minus 2, which is 1. All right, divided by time span, which is also 3 minus 2, which is 1. So my acceleration is 1 meters per second squared. And you will notice that, similarly to DT graph, the slope of the line in a VT graph gives you the acceleration. All right, so the steeper the line, the greater the acceleration, because given a period of time, the velocity will change a lot compared to a less steep graph. So right, this is the change of velocity of this curve, this is the change of velocity. Basically, the steeper the graph, the more change the velocity in a given period of time, which means the greater the acceleration. So this is intuitive and it makes sense, right? All right, now the real life situation is that the velocity of an object does not always change proportionally to time, right? So it might look like this. Initially, it goes up, goes down, it goes all curvy, right? So how do we calculate the acceleration here? Well, it will be different for every moment, right? So we need to distinguish two very important concepts, which is the average acceleration and the instantaneous acceleration. All right, so the average acceleration measures the acceleration averaged out between 2 points. For example, we want to calculate the acceleration between 0 and 2 seconds. What we do, we just take the value of the velocity. Well, they are respectively 2.5 and 3. First thing, we take the difference of the velocity, which is 0.5 meters per second, divided by the time, which is 2 seconds. Well, we got our average acceleration, which is 0.25 meters per second square, right? So this is the average acceleration. And you will notice that this average acceleration is basically the same thing as if the object is traveling at uniform acceleration, which means its acceleration is the same all over span of time between t equals 0 and t equals 2. However, on this graph, we notice that initially the acceleration was greater than 0.5 meters per second because it has a steeper slope, right? And at t equals 1, it started to decelerate. Its acceleration is negative. So the acceleration between t equals 0 and t equals 2 does not always equal to 0.5 meters per second squared, 0.25 meters per second squared. It's different. So that's what we're going to introduce, the instantaneous acceleration. So the instantaneous acceleration measures the acceleration at one moment, so not between two moments. All right, so for example, I want to measure the instantaneous acceleration at t equals 0. Well, it's obviously the slope of this line, which is, say this is 5. This will be, 2.5 divided by 1, which is 2.5 meters per second squared. So the average acceleration between 0 and 2 is 0.25 meters per second squared. However, the actual acceleration, the instantaneous acceleration at t equals 0 is 2.5 meters per second squared. And why is the average acceleration lower than this? Well, because between t equals 1 and 2, the acceleration is negative. And that negative and this very big positive, they balance out to become this average number, right? So this is the thing you need to remember. Now, this is the straight line case. How about the real life case where, the VT graph gets all curvy? Well, it's basically the same thing. If we want to measure the average acceleration between two moments, we'll just take the difference of the velocity, delta V, we divide it by delta T, right? So that gives us the average acceleration between 2 points, which is the same as the object taking uniform acceleration between those two moments. However, if we want to measure the instantaneous acceleration, it's a little bit more tricky. Let's see now we want to measure the instantaneous acceleration at t equals 2. Well, what do? We cannot just look at the graph and say it's acceleration. However, we know how to measure the average acceleration between any two moments. So, first of all, let's measure the average acceleration between t equals 2 and 3. Well, that will be the straight line connecting those 2 points, the slope of the straight line connecting those 2 points, right? The delta V divided by the delta T, right? So, the average acceleration won't be quite the actual acceleration at the t equals 2. So what we do is we instead measure the average acceleration between t equals 2 and t equals 2.1. Well, that average acceleration will surely become closer to the actual value, to the actual acceleration at t equals 2, because that slope will be. And what we do is next, we measure the average acceleration between t equals 2 and t equals 2.0001. And we measure on and on and on, just like that, until that point, that second point that we take to measure the average acceleration is super duper close to t equals 2, then we say the average acceleration between t equals 2 and t equals 0.1 is the actual acceleration at t equals 2, right? So, imagine I started here. This is the average acceleration, and now it becomes this, and now it becomes this, now it becomes this. It's approaching, and finally, when it couldn't be closer, the average acceleration will be the slope of this line, right? So the slope of this line, you will notice, is actually tangential to our graph. Thus, we can say that the instantaneous acceleration at any point on the graph is just the slope of the tangent line at that point, right? So the tangent line, if you didn't know, is the line that just touched one point on the graph, all right? So first thing, it only touched one point on the graph. Second thing, it cannot cross the graph, all right? So it cannot cross the graph, it can only touch one point. That's the tangential line. All right, so for example, what's the instantaneous acceleration here? Well, it's the slope of the tangent line, which is this, right? So basically calculating is like 2 meters per second squared, right? So you can see, because on every point we have a different slope of the tangential line, the acceleration on every point is gonna be a little bit different. All right, it's gonna be a little bit different. All right, now let's look at a work example of acceleration. All right, so this is the VT graph of an object. All right, you will notice that some of the curve goes through the negative portion. This just means the object have negative velocity, which, let's say, the positive direction is to the right. So in these time, the object is traveling to the right, and in these negative time, they are traveling to the left instead. All right, so I have the curve of VT graph, and I want you to draw the curve of the AT graph of this object. So I want you to draw the curve that gives you the information of the acceleration of the object at every moment. All right, so this is a pretty hard question. Let's look at it together. Alright, so we know acceleration is the change of velocity, and we are talking about instantaneous acceleration here. So we're looking at the slope of the tangent at every moment. Alright, so what's the slope here? Well, it's like this. So the slope here is actually kind of close to 0, right? And now it starts to go down, be more negative, and now it started to go to not that negative. So it went back up like a little bit, and it stays constant for a while, and at here it continues to approach, and at here it becomes flat, right? So the tangent becomes flat, so at here it should become 0. So the acceleration at this point is actually 0, and then it starts accelerating to the right. So accelerate, 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 finally until this point where its acceleration becomes 0 again. So its acceleration is positive, positive, positive until it becomes 0 at this point. So it makes sense, right? And it starts rapidly decelerating. It starts rapidly going to the opposite direction. All right, so the acceleration will go down very negative, and on this point it becomes 0 again. It doesn't accelerate. So the acceleration go back to 0 again, and then it starts to accelerate again. We are drawing the tangent, and we're looking at the slope. The slope become positive again, so the curve goes right back up. So this is the AT graph. So this is the AT curve of this object. This blue curve gives you the information of the acceleration of the object at every moment.